we will be using the combined gas law in Chapter 10, Section 10.4 in order to make calculations. The combined gas law is given to you in the box. P1 times V1 divided by T1 will equal P2 times V2 divided by T2. You should know that before, the 1 is showing you the conditions before, and the 2 is describing the conditions afterward. So with a given initial pressure, volume, and temperature, if we were to say change the temperature, then that'll affect what the new pressure and volume would be. There are several rules that need to be adhered to when doing these calculations. If pressure, volume, or temperature are constant, then they cannot be a variable, and therefore we ignore them in the calculation. So, for example, if you were told that the temperature is constant, then we would ignore temperature, and our equation would then be P1 times V1 equals P2 times V2. Another example would be if you were told that the pressure is constant, then we would ignore the pressure, and your new equation would become V1 divided by T1 equals V2 divided by T2. If none of the variables are constant, then you will use the entire equation as it is. The second rule, probably one of the most important, all calculations must have Kelvin as the temperature's unit. So you cannot perform the calculation unless your temperature is in Kelvin, and I will highlight this because it's that important. Temperature must be in Kelvin. Temperature must be in Kelvin to solve all equations. Okay? The third rule, your pressure and your volume units must be consistent. That means that they just need to match. They need to be the same. So if you have one pressure in atmospheres and one in torr, you're going to have to convert one of them to match the other. It doesn't matter what unit they're in as long as they match. And lastly, if you come across a problem that states STP, it means use standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere as part of your calculation. So we're going to do a few practice calculations. We're going to use the following method. Convert your given, solve the equation, then you might have to convert your answer. Remember, you may or may not need to do all three of these parts. Guaranteed, you have to do the center part, which is solve the equation. You may have to convert the given, you may have to convert the answer. It depends on the situation. So we'll start with number 1. And we're going to highlight our givens. A sample of gas occupies a volume of 8.50 liters, 0.988 atmospheres, and 25 degrees Celsius. What is the temperature in degrees Celsius if your new volume is 4.00 liters and the pressure is constant? So normally, the way you begin setting up these problems is identify your variables. V1, P1, T1, V2, P2, and T2. So V1 is 8.50 liters. They give you an initial pressure of 0.988 atmospheres and an initial temperature of 25.0 degrees Celsius. Immediately, you want to go ahead and add 273.15 to Celsius to change it to Kelvin, because all calculations must be in Kelvin. So that's 298.15 Kelvin for my temperature. Okay, my second volume given was 4.00 liters. They told me the pressure was kept constant, which is very important, and therefore means we will not use pressure at all in this calculation. So we're going to get rid of pressure. Lastly, they're asking me to solve for temperature. What is the temperature? You need to understand that when you perform this calculation, you're going to get your temperature unit in Kelvin first, and then we're going to have to convert it to degrees Celsius at the end. So in this case scenario, we are going to, we've already converted our degrees Celsius to Kelvin. Now we're going to solve the equation, and at the end we'll have to convert our answer from Kelvin to Celsius. The equation that's going to be used is P1V1 over T1 equals P2V2 over T2. However, because pressure is constant, we're not going to keep pressure in the equation, which makes our new equation actually V1 divided by T1 equals V2 divided by T2. We're going to substitute. V1 is 8.50 liters divided by a temperature of 298.15 Kelvin equals your second volume, 4.00 liters, divided by, and we're trying to solve for T2. Since T2 is what we're trying to solve for, we're going to use a method called cross multiplying. You will start by multiplying 4.00 times 298.15. 4.00 times 298.15. You will then divide by 8.50. This is going to equal your second temperature. So we'll take 4.00 times 298.15, and that's going to be divided by 8.50. This gives us 140.3. We want to watch our sig figs. Our givens are all 3 sigs, so I want this to be 140 with a decimal running after it. So this will equal 140 with a decimal. And so far, this is in Kelvin. Keep that in mind. It's going to be this same temperature unit. Temperature 1 is in Kelvin, so temperature 2 is officially in Kelvin as well. Now, we want to go ahead and do our final convert, because we need this to not be in Kelvin, we need it to be in Celsius. So degrees Celsius will equal my Kelvin temperature minus 273.15, and that's going to give us a temperature of negative 133. And that is now in degrees Celsius. Number 2, the volume of a gas is 250 milliliters and a pressure of 245 kilopascals. What will be the new volume if the pressure is reduced to 80 kilopascals and temperature is constant? So this means we will not need temperature. So first we'll identify our variables. P1 equals V1 equals T1 equals, P2 equals V2 equals, and T2 equals. And I'll go back now and remove temperature. Since temperature is constant, we won't need it. We are given a first volume of 250 milliliters, a pressure of 245 kilopascals. What will be the new volume? They don't specify, so whatever my first volume is, that's what my second volume will be. And then they give me a second pressure of 80.0 kilopascals. My equation is going to be P1 V1 over T1 equals P2 V2 over T2. However, since temperature is constant, we will not be using temperature in this equation. So that makes my equation now P1 times V1 equals P2 times V2. So now I'll go ahead and plug in what I have. 245 kilopascals times 250 milliliters equals 80.0 kilopascals times V2. We are solving this equation with algebra for the second volume. So in order to do this, I want to divide both sides of my equation by 80.0 kilopascals. On the right, my 80 cancels, leaving me with just V2 equals, and then I'm going to do my math. 245 times 250 divided by 80.0 gives me 766. And we want to use 3 sigs because all my givens have 3 sig figs. So 766. And because my original unit was in milliliters for volume, then my unit for my answer is also going to be in milliliters. This container is 3.50 times 10 to the 5 meters cubed with a temperature of 27 degrees Celsius, a pressure of 115 kilopascals. What is the new volume if the temperature drops to -10, the pressure drops to 99? So we do have a lot of converting to do in this one. We have P1 equals 115 kilopascals. V1 equals 3.50 times 10 to the 5 meters cubed. And T1 equals 27.0 degrees Celsius. Immediately, I will take Celsius, add 273.15 to change it to Kelvin. And that'll give me 300.15. My P2 is 99.0 kilopascals. My V2 is what I'm trying to find, and my T2 is -10.0 degrees Celsius. Immediately add 273.15, which is going to give me 263.15 Kelvin. Notice that both of my pressure units are in kilopascals. So since those match, I don't have to change them. And both of my temperatures are now officially in Kelvin. So since those match, I don't have to change them either. Notice that your volume is in meters cubed, which is automatically going to make your answers unit in meters cubed as well. So now that I have that established, let's see what our equation is going to be. P1 V1 divided by T1 equals P2 times V2 divided by T2. Nothing is constant, so we will be using every number for this calculation. My P1 is 115 kilopascals times 3.50 times 10 to the 5 meters cubed divided by my first temperature, 300.15 Kelvin, which is going to equal my second pressure, 99.0 kilopascals, times, I don't know what V2 is, divided by my new temperature, which is 263.15 Kelvin. 115 times 3.50 e to the 5 times 263.15. Then we want to divide by 300.15 and 99.0. So we're going to multiply by what's in yellow, and then we're going to hit divided by each number that's in green. So we will hit 115 times 3.50 times 10 to the 5 times 263.15 divided by 300.15 divided by 99.0. This gives me a very large number, which I'm expecting. And so that'll be 356,448. 356,448. This is meters cubed, and if I want the correct significant figures, I'm going to use 3 significant figures, which gives me 356,000 meters cubed as my new volume. This is the same thing as 3.56 times 10 to the 5 meters cubed, which you'll notice is our answer in the parentheses.